And the recording is live. So today's topic, we are starting off with the idea of stoichiometry. Whoops, that's a big. Stoichiometry spelled Stoichiometry. Stoichiometry. It is sometimes referred to as mole ratio. The two phrases can be thought of as interchangeable. Now, the idea behind stoichiometry is simply ratios and proportions. I think of, for example, if we were to look at a cooking recipe online, most generic recipes will, for example, say, oh, this can serve up to 4 to 6 people. If you'd like to increase the serving size, just adjust portions correctly. If you've ever done anything like that, then you understand the basics behind stoichiometry. But to really lay it down flat, I want to make a sandwich. Now, a sandwich is comprised of, let's say, 2 slices of bread. I promise I'm going somewhere with this. 2 slices of bread, 1 slice of cheese, let's say 3 slices of deli meat. And in total, this gives us 1 sandwich. When written in this way, it's a lot easier to draw analogs to cooking and reactions. We have here on the left-hand side the reactants, the ingredients, and over here on the right side we have the products. Similarly to what we've been used to are those coefficients in front, those big numbers that talk about balancing. The balancing, of course, tells us how much of each reactant, how much of each ingredient we need in relation to the product. From this, we're actually able to build a ratio very simply that for every 2 slices of bread, we need 1 slice of cheese, we need 3 slices of meat, and all in all, this will get us 1 sandwich. These ratios become important because without actually having to do the work, we can make predictions. For example, if we go into the kitchen, we see that we have 4 slices of bread. That means we can make 2 sandwiches. How did I come up with that? Look at that ratio. That's a 2-to-1 ratio. For every 2 slices of bread, I can make 1 sandwich. So if I have 4 slices, I can make up to 2. Similarly, to make 2 sandwiches, I need 2 slices of cheese. But both perspectives work, however. You could say, well, if I have 4 slices of bread, then again here I have a 2-to-1 ratio, so 2 slices of cheese. Or you could have recognized, well, the ratio between cheese to sandwich is 1-to-1, so 2 slices of cheese, 2 sandwiches. And then, of course, finally, to no one's surprise, if we're making 2 sandwiches, if we have 2 slices of cheese and 2 slices of bread, we'll have up to a total of 6 slices of meat. This right here is the fundamental idea behind stoichiometry. Ratios, that the amount of one reactant affects the amount of another reactant. Similarly, if we want to make a certain amount of product, let's say that we intend on making 3 sandwiches. We can foresee the future. We know to make 3 sandwiches, we're going to need 6 slices of bread, 3 slices of cheese, 9 slices of meat. So the idea behind stoichiometry is we're able to make predictions about one ingredient or chemical based on information about another. So in essence, it is making predictions about one chemical based on information from another. Based on information about another. Let's keep that about going. This is the essence of stoichiometry. Now, a couple of weeks ago, almost to the date, we introduced what was known as the mole concept. And way back when we talked about the mole concept, we talked about the mole being chemical currency. It is the simplest way to describe chemical amounts in a way that everyone understands, just like how the dollar is used instead of, for example, nickels, quarters, and dimes. Way back when, we also covered that the molar mass of anything is equal to 1 mole of anything. We similarly said that 1 mole of anything was also equal to Avogadro's number, 6.023 times 10 to the 23 atoms or molecules. Under this same topic, I taught you about 2 primary formulae. N is equal to M over MM. And N is equal to capital N over N sub A. Way back when, I had instructed you that N refers to moles. Lowercase m refers to the mass of the sample. MM is molar mass. On the right side equation, N is the same, N is moles. Capital N is number of particles, where particles is thus the generic term for atoms / molecules, the number of particles. And N sub A is Avogadro's number, 6.023 times 10 to the 23. This is everything we covered about 2 weeks ago. The mole is chemical currency, the relationship between mass, mole, and Avogadro's number, as well as the 2 equations. Today, we are introducing the beginning stages of what I like to call the roadmap. You see, we know that for a generic chemical X, we can relate the mass of that chemical to the number of moles of that chemical. In fact, the relationship between the two is based around molar mass, where m is lowercase m, moles is lowercase n. And just as a reminder of the formula, N is equal to M over MM. You see, this is what we just talked about. This is what we just recalled. We know there is a relationship between mass and mole. Now we're just kind of making it a little bit more visual. We can do the same thing, make a similar visual map for chemical Y, aka just another generic chemical. Where again, we can relate the mass of chemical Y to the moles of chemical Y in this way. But today, we have introduced the link between chemical X and chemical Y. Let's use a different color. Someone pick a color, not black, not red. Orange. Oh, wait, I heard orange first. Connecting the 2 chemicals is stoichiometry, aka mole ratio. What this roadmap allows us to do is that it allows us to visually track the information in a question and identify, well, for lack of a better word, the path ahead. I actually like to think of these boxes as stops along a bus line, and what's between the arrows as our bus pass. In other words, to go from A to B, you need molar mass. To go between A and C, you need stoichiometry. And to go between these two final boxes, of course, is just molar mass. Now, what exactly does this look like? What does this mean? How do we use this? Well, let's find out. Here's a question. Oh, whoops, it's moved up too much. Based on the chemical reaction shown here, aluminum solid plus HCl aqueous gives us aluminum chloride aqueous added to H2 gas. Now, we had a lot of practice on reactions on Friday, so hopefully we're all able to look at this reaction in full and understand where every single bit comes from. You should understand why it's H2. You should understand why there is a 3 after the AlCl3. And of course, you should be able to understand where the states come from. It's not balanced as of yet. That's on purpose. Question A says, how many moles of aluminum are needed to produce 0.334 moles of AlCl3? Okay. Let's think about what the question's asking us. We're being asked information about one chemical and being given information about another chemical. The fact that I'm able to summarize this question in this way is the immediate proof that we will be using the roadmap. So I'll give you time to kind of draw the map yourselves. We know what it looks like on the board, and I'm of course having it up on this on the projector. All right, based on the question at hand, we are comparing aluminum to aluminum chloride, so chemical X, chemical Y, aluminum, and aluminum chloride. It does not matter left or right. You could have chosen to put AlCl3 on the right and just Al on the right. I'm sorry, you could have chosen to put AlCl3 on the left and Al on the right. It wouldn't matter. The choice is yours, left or right. They're just meant to represent generic chemicals. We know that our roadmap is ultimately between aluminum and aluminum chloride. Based on the wording of the question, it asks how many moles of aluminum. We know that moles is N, so we know what the question is asking for is this box right here. We visually indicate it with some question marks. That's what we're trying to find based on the wording of the question, that it says how many are needed to produce that much of aluminum chloride. So we are given some information, so let's fill that in. 0.334. Looking at the roadmap clearly tells us that to find this guy, the question mark, we're just going to traverse between moles. That's what the roadmap tells us. In other words, the mass is not needed. It's just not part of the map. So to make it simpler on us, we're just going to go ahead and erase that top half. You, of course, can leave it in your notes, of course. I just want to make this a little less congested. And ultimately, we know what we're missing. The bus pass we need is mole ratio. Now, mole ratio, of course, is based on those balanced numbers. We talked about the sandwich analogy. So the first thing we need to do is, of course, balance the given reaction. Hopefully, we're at the point where I should be able to say this pretty quickly. We're going to have 2 aluminums, 6 hydrogen chlorides, 2 AlCl3s, and 3 hydrogens. Look for yourself to confirm you understand these numbers and where they come from. All right. Between aluminum to aluminum chloride, we can see that the mole ratio, that the ratio of reactant and product is 2 to 2. We can see that for every 2 aluminums, we will make 2 aluminum chlorides. That means for every 3 aluminums, we'll make 3 aluminum chlorides. 4 to 4, 5 to 5. This 2 to 2 can actually be simplified to 1 to 1. They're in the same ratio. Based solely off of that logic, does anyone want to take a guess how many moles of aluminum are needed? I see a hand. 0.334. What did we do here? We used the roadmap to identify what we needed to figure out and how to get there. We identified we'd be using mole ratio. We balanced the equation, identified 1 to 1, and made the very quick statement 1 to 1, therefore 0.334 moles are needed. That right there is our final answer. That makes sense. I mean, if we were to think back to the sandwich analogy, how many slices of cheese do you need to make one sandwich? Well, what did we do? We just looked at the ratio, 1 to 1, the same number. But what if it starts to get a little bit more complicated? Part B. We will need the reaction again, so I'll just quickly write it up here. We have 2 aluminum solid added to 6 HCl. Whoops. To give us 2 aluminum chloride plus hydrogen, 3H2. Question B says, how many grams of HCl are needed to react with 0.545 moles of aluminum? Okay. Let's think about what the question's asking. So we see here it's asking us information about one chemical, HCl, how many grams of it, and it's given us information about another chemical, 0.545 moles of aluminum. That alone tells us we will be using the roadmap, adjusting the one we used most recently for this one. Let me just make some erasing. We know we are comparing HCl and aluminum based on the wording of the question. Again, it doesn't matter which one is left, which one is right. The wording of the question says, oh, how many grams of hydrogen chloride? So we know that's what we're trying to find. So we'll put a question mark in there. And we're told that we're working with 0.545 moles of aluminum. Please notice, to the best of my ability, your numbers should line up with the relevant chemical. That's why it ultimately doesn't matter which side you put what, as long as the question mark and the numbers are on the correct side. All right, so let's go take a bus ride. We're starting at moles. We see that to get to our final destination, where are we going to go? We're going to go from mole ratio. Then we're going to go moles to mass. 2 different steps. We're going to first use mole ratio to get the moles of HCl. That's step 1. And then from moles to mass of HCl, that's step 2. This is the point where it's important for me to mention explicitly, the roadmap is ultimately a visual tool that's used to gather your thoughts. One of the biggest struggles of stoichiometry, and I'm speaking to anyone who's either taken this class before, maybe you've seen this topic before, you know that the hardest thing about this topic is figuring out, what the hell do I do? How do I know what to start with? How do I know where to go? The roadmap is our visual gathering of thoughts and numbers that tells us mole-mole ratio, moles to mass. It is ultimately a visual tool that's used to consolidate the information. Now, we can tell based on the roadmap, the path ahead does not need this box up here. So just for ease of clarity, let's erase it. We don't need that box up there. What do we need? We see we need the bus pass. We need the mole ratio. We need the mole ratio between HCl and aluminum. That's right up here. We see that the mole ratio is 6:2. Where did that come from? There are 6 HCl's and 2 aluminums. Now I want to stress something. Do note the order. I arbitrarily wrote HCl on the left. That was my choice, but I have to remember to put its stoichiometry on the left as well. In other words, 2 to 6 would be wrong because you're implying there are 2 HCl's and 6 aluminums, which is in fact not what happens. So although the label is your choice, just remember your stoichiometry has to match the order. Now, 6:2, that can be actually further simplified to 3:1, just to get it out of the way. We will eventually calculate this, but we see the next bus pass we need is the molar mass. We need the molar mass of HCl. That's something we can very quickly calculate. The molar mass of HCl is equal to the mass of 1 hydrogen added to 1 chlorine. That's 1 gram plus 35.5. This is approximately 36.5 grams. To quickly update the roadmap, we can see our exact numbers. We have now filled in the roadmap. No calculations have begun. All I have done is fill in the roadmap based on information from the question and things I can very easily determine, aka mole ratio and mass. Now, guess what? I'm going to hide the question because everything I need is in the roadmap. It's my visual tool to know where to go. First things first, I have to go use mole ratio. That's going to be step 1. Now, there is no explicit formula for mole ratio, so you do have to put in a little bit of math effort. Here's how it looks. We are comparing hydrogen chloride to aluminum. We know that the mole ratio between the two is 3:1. We know that. That is the bus pass we use. We know it for sure. What we don't know, our unknown, is how many moles of HCl do we use or need based on 0.545 moles of aluminum. We have set up this ratio. It's a nice 2x2. It looks like a table. Here's what we're going to do. We're going to cross multiply. This tells us X is equal to 3 times 0.545. All right, now pause. Those of us in here who are math inclined, you may be looking and thinking, Supreet, I didn't really need to write that down. I could have just recognized 1 to 3 and did that. That's fine with me. If you're very comfortable with the math and you can do this in your head, that's fine with me as long as the answer is correct. That's all that matters. But if you are not comfortable with the math, I will always recommend you break it down like this. Comparing two chemicals. We know the mole ratio. What we don't know are the exact numbers. Putting this into our calculator. We'll grade this. 0.545 times 3, that's roughly equal to 1.635. We're not done yet. All we've done is calculate the number of moles. That was step 1. The path ahead then says to go from moles to mass is step 2. From moles to mass. Let's look at the roadmap. Remember, the roadmap tells us everything. It tells us to go from moles to mass. We will be using the formula shown here. We already know N, and we previously calculated the molar mass. This is the beauty of the roadmap. Once you fill it in correctly, everything from there just falls into place. That's how we know that N is equal to M over MM. We're trying to find M. So M is equal to N times MM, where N is 1.635 and the molar mass is 36.5. We put this into the calculator. 1.635 times 36.5. That's roughly equal to 59.68 grams. And this right here is our final answer. As you practice, I do recommend just recognizing you do not have to update the roadmap the full way, but you can. On the exam, I won't be looking at your scratch work, right? I'll only see the final answer. Questions? I see a question. Yeah. That's an X, just meant to represent a generic. You could use A, B, C. I just use X. I see a hand over here. Yeah. The molar mass was something we just calculated earlier. The molar mass of hydrogen is the mass of hydrogen added to chlorine. Refer to our periodic table. Hydrogen's mass is 1, chlorine's is 35.5 for a total of 36.5. Yeah. Yes, it'll all depend on my instructions on the exam, round to whatever decimal places. But yes, for the most part, we'll stick to 1 decimal place here. Yes. Yes, I could put that on the exam. Yep. Any other questions? Okay. Next up, reaction metrics. Reaction metrics are our quantitative way of measuring a reaction. In a lot of ways, when we discuss reaction metrics, we are referring to the success of a reaction. The primary metric of a reaction that we will use is known as percent yield. The percent yield of a reaction, as clearly as it says a percentage, can be thought of as a score for the reaction. The formula is actual yield divided by theoretical yield, abbreviating yield to Y for the denominator, multiplied by 100 since it's a percentage. It's important to understand the key difference between actual yield and theoretical. Actual yield is how much of a chemical is actually made, keyword actually, made in the experiment. So this is not a value that you could, determine or calculate. This is the value you get after you do the experiment, after you do your weighing. The theoretical yield is the value you calculate. Specifically, what you calculate using the roadmap. The subtle difference there, just depending on the perspective, of course. Actual, whoops, that was an erasing. Actual yield is how much is actually made in the experiment. That's how much you determine after you finish. And then the theoretical is something you can outright calculate. Let's do part C of that reaction. 2 aluminum added to 6 HCl gives us 2 aluminum chloride plus 3 H2. Part C says, what is the percent yield if 0.25 grams of H2 are actually, keyword actually, made. Whoops. If 3.33 grams of aluminum are used. Okay. So ultimately, the question is asking for the percent yield. Percent yield's formula is actual over theoretical. I have told you that 0.25 grams of hydrogen are actually made. So we already have our actual yield. And I've given you information about another chemical. All that's left is to calculate the theoretical yield. Remember, that's what you calculate using the roadmap. The roadmap connects to chemicals, the chemical with information you know. So we are now going to do another roadmap. And in this roadmap, we are going to connect aluminum and hydrogen. Question for the crowd. Am I going to put that 0.25 anywhere in the roadmap? No. Why? It is the actual yield. It is not something we're really concerned with calculations because it's how much is actually made. So no point at all will that 0.25 appear in the roadmap. 3.33 grams of aluminum. All right, we can fill out what's left of the roadmap. We know, of course, ultimately we need the theoretical yield. So we know we need the mass of the hydrogen. That's the theoretical amount made. What else can we need? We know that the path ahead says mass to moles, mole ratio, moles to mass. So we're going to need a couple things. We're going to need, for example, the molar mass of aluminum. That can just be gotten straight from the periodic table. That is 26.98, just straight from the periodic table. We also need to know the mole ratio between aluminum and hydrogen. Aluminum and hydrogen is right here. We see that there are 2 aluminums and 3 hydrogens. So the ratio is 2 to 3. That cannot be simplified anymore, so we keep going. Finally, the last thing we need is the molar mass of hydrogen. There are 2 hydrogens, so 2 times 1 gives us approximately 2 grams. And with that, I have completely filled out the roadmap. Now I'm going to stop looking at the question, stop looking at the reaction. Everything I need is in the math. The bottleneck to your success on these kind of questions is filling in the roadmap. If you make a mistake filling it in, no matter what, your calculations are going to go wrong. So have patience, take your time, fill in the roadmap to the best of your abilities. The path ahead becomes clear. First things first, mass to moles, mole ratio, moles to mass. Let's do it in order. Step 1, we are converting mass to moles for the aluminum. Do note how I like to, do my math. I like to take these kind of notes, make these kind of headings, because when I review my notes, sometimes I forget what I did, right? Having these kind of labels helps you in your review so you can understand what your thought process was. So the very first step, we're going from mass to moles for aluminum. Moles is equal to M over MM. We already know the mass, 3.33. We already know the molar mass, 26.98. We put this in our calculator, 3.33 divided by 26.98 gives us approximately 1.1234, angel numbers, cool. 0.1234. Okay, I can choose to continue filling in the roadmap so it helps me visualize where I'm going. After I get moles, I'm going to say mole ratio. Step 2 is mole ratio. What am I doing? I'm going to compare aluminum to hydrogen. I know, here represented as K, I know that the ratio is 2 to 3. I know that. That's from the balanced equation. What I don't know is if I have 0.1234 moles of aluminum, how many moles of hydrogen do I need? Here we have our 2 by 2, our nice ratios. We're going to cross multiply. This becomes 2x, 2 times x is equal to 3 times 0.1234. To get rid of the 2 on the 2x, we're going to divide both sides by 2. Now let's put this in our calculator. 3 times 0.1234 all over 2. Our number here is 0.81851. Continue to fill in our roadmap just so we can keep track of everything we've done so far. I've run out of space on this page, so I'm going to have to move over to the next one. 1 second. Our final third step is to go from moles to mass, specifically for hydrogen. So this is moles to mass for hydrogen. The formula is N is equal to M over MM. With a little bit of rearrangement, we know that M is equal to N times MM. The number of moles, it's in the roadmap, that's 0.1851. The molar mass, we previously spent time to calculate. That's going to be 2 grams. Put this into our calculator. We get 0.3702 grams. Now, technically speaking, we're not done yet. Remember what the original question was all about. It was about percent yield. Percent yield, here abbreviated as percent Y, is equal to the actual yield divided by the theoretical yield, abbreviated to AY and TY, respectively. The actual yield, that was told to us in the question. 0.25 grams of hydrogen are actually made. The theoretical yield, that's what we just spent all of our time doing. Take note of that. Ultimately, we knew the question was about percent yield. Percent yield is a fairly straightforward formula. I've given you the actual yield, but we spent a lot of time determining the theoretical yield. That's that 0.3702 number times 100. Putting this in our calculator, 0.25 divided by 0.3702, all of this times 100. We get approximately 68%. Remember that percentages are traditionally rounded up to the nearest whole number. 68% is our percent yield. So if someone were to ask you, how successful was this reaction? You could simply say, it had a 68% yield. Now, the concept of yield being a measure of success is something that's a bit nuanced to understand. Because we can easily say that if the yield is less than 100%, most likely the reaction is unfinished. Maybe it has somewhere to go, maybe it just needs extra time. If the yield is a perfect 100, then that's what we call a success. But occasionally, you can get greater than 100% yield. That simply means something went wrong in the experiment. It's not a problem. It's not something for you to fix. It's not something for you to worry about. But don't be surprised if you do some questions and your yield is over 100. It happens. It's just a reflection of the success of the reaction. Less than 100 means probably needed a little bit more time. Maybe some more of each product, of each chemical. A perfect 100 means great. That's what we want. That's a successful reaction. Over 100 simply means something went wrong. No big deal. It's just a reflection of the experiment. Questions? Yeah, I see him. Is that Paul? Yeah. They are incredibly rare, but they do happen. I will say that when they do happen in the peer review process, they do vet it. They do like say, hey, prove it to us that it's actually 100. We need proof of that. It is something that scientists are like, I'm a little doubtful, but if you give me a whole bunch of evidence, I'll accept it. But it's possible. Any other questions? This is a big topic. This is wildly different from last week's topic of reactions. That's why this Wednesday is our designated in-class problem set on this topic. I'll come with a worksheet. We'll work on questions together. You'll have some to do on your own. Thursday. Yeah. Oh my God. I'm so sorry. That's happened twice now. I don't know why I keep thinking it's Monday. I think it's because last semester I taught this class on a Monday, so I'm kind of going back into my rehearsed lesson from last year. Okay. Let's try a new question. Based on the following reaction. This is the reaction between carbon and sulfur. Which results in the product CS2, which is also a gas. The question is simple. Determine the theoretical yield of product the theoretical yield of CS2 when 12 grams of carbon reacts with 23 grams of S2. Okay. Let's think about what this question's asking us. Actually, before we do that, let's just be sure that the reaction is balanced. Yes, what's your question? I'm sorry? Determine the theoretical yield of CS2. Oh, I see. I forgot the when. I see. When 12 grams of carbon reacts with 23 grams of sulfur. Thanks for catching that. First, let's ensure the reaction is balanced. 1 carbon, 2 sulfurs, 2 sulfurs. So the reaction is balanced as given. It just so happens to be 1 to 1 to 1. Remember that it's always your duty as a student to make sure the reaction is or is not balanced. Sometimes they are, 1 to 1 to 1. So the question says, determine the theoretical yield of CS2 when 12 grams of 12 grams of carbon reacts with 23 grams of sulfur. Okay, now this one's a whammy because I'm asking you information about one chemical, but I've given you information about 2 chemicals. This is new. I've always only ever given you just 1. Now I'm giving you 2. So what do we do with that? Regrettably, you're going to draw 2 roadmaps. You're going to draw a roadmap connecting each reactant to the product. And we're going to do 2 roadmaps in total. Whoa. Mass, moles, mass, moles, mass, moles, mass, moles. I'm just writing up the roadmap now. Don't forget it. A copy of it is on the board. I'm just kind of drawing that chart in. All right. Before I even start working on any calculations, we can fill in the roadmap based on the questions in front, based on the question. It's ultimately asking us for the theoretical yield of CS2. So we know ultimately that's what we're being asked to find. So that's where we can put our question mark. We're told we're dealing with 12 grams of carbon, 23 grams of sulfur. So we can put 12 right here, 23 right there. The path ahead in both cases is the same. Mass to moles, mole ratio, moles to mass. Mass to moles, mole ratio, moles to mass. In our attempt to get there, we need a couple bus passes. Just filling over here first, we need the molar mass. We need the molar mass of carbon. That can just be gotten from the periodic table. That's approximately 12 grams. Next up is the mole ratio between carbon and carbon disulfide, CS2. For that, we're just going to refer to the reaction. We know already that's 1:1. So we just make a note of that, 1:1. We need the molar mass of the carbon disulfide. That's 1 carbon added to 2 sulfurs. Carbon has a mass of 12. Each sulfur has a mass of approximately 32. This is 12 plus 64 for a whopping 76 grams. I can do the same thing over here. The molar mass of sulfur, there are 2 sulfurs, each of which is 32 grams. So we have here 64 grams. We know the mole ratio between sulfur to CS2. That's already been established as 1:1. So just rewrite it. And then fortunately, we already spent time with the molar mass of CS2. So we can just write that down, 76 grams. Now that I've filled in the roadmaps to the best of my ability, guess what? I'm done looking at the question. I'm going to trust myself. I'm going to trust the math. I'm going to work on these roadmaps. I'm not going to do both in tandem. I'm going to do the left side first. I'm going to draw this line all the way down. Let's work on the left side first. The first thing we need is to go from mass to moles. Number of moles is equal to mass over molar mass. The mass we see here is 12 grams. We know the molar mass is 12 grams. This is a very easy one. Twelve divided by 12 is 1. Within the roadmap, we continue to fill it in. This is a very simple ratio. This is just 1:1. So no real guesswork here. Let's write the 1. See, remember, I won't be looking at your scratch work. I'll only be looking at your final answer. If you're strong enough in math to do this ratio part in your head or on your calculator, no problem with me. Just make sure it's right. 1:1 is the easiest case, though. Finally, we're going to go moles to mass. Mass is equal to number of moles times molar mass. That's 1 times 76. That's a whopping 76 grams. So based on carbon, we can make 76 grams of CS2. That's one roadmap out of the way. Now we're going to do the one on the right. Process is the same. First thing we're going to do is mass to moles. Number of moles is equal to the mass divided by the molar mass. That's 23 divided by 64. Putting this into my calculator, 23 divided by 64 is approximately 0.36. Sorry that calculator disappears so quickly. I wish I could fix that. 0.36 moles. Quick recognition that the ratio is 1:1. 0.36 moles again. The final step is to go from moles to mass. M is equal to N times MM. This is equal to 0.36 times 76. All right, put this in our calculator. We have 0.36 times 76, 27.36. Therefore, we know that based on sulfur, the 23 grams, we can make 23.6 grams of product. Here's the big thing you need to know. The lesser amount of products is the theoretical yield. The lesser amount of products is the theoretical yield. I'm telling you this is a fact. So, based on the two reactants, we can either form 76 grams of carbon disulfide or 27.36. I'm here today to tell you that the lesser amount is the theoretical product. This is what tells us 27.36 grams of product is our final answer. Now, why does this make sense? Why did we make this approach? Why did we do two roadmaps? Why did we have to do all of this effort? To understand a little bit more about that, I would like to go back to the sandwich analogy really quickly. Now, let's say you come home and you and your friends are at home and you guys have played at the park or whatever you do. And your friends are like, hey, could we get some sandwiches? We're a little hungry. So you, being the good host that you are, what do? You go back and you check your pantry. And within your pantry, you see, okay, I have, it looks like 6 slices of bread. I have about 2 slices of cheese and approximately 6 slices of deli meat. So you go check in your pantry. You go and see how much of each ingredient you have. And you say, based on the bread, I can make 3 sandwiches. Right? Remember that ratio 2:1? Based on the cheese, I can make 2 sandwiches. Based on the meat, 2 sandwiches. So are you going to go back to your friends and tell them, hey guys, I can make you 3 sandwiches? You're going to tell them you can only make 2. How did you know that? You evaluated each reactant, so the amount of product you could make, and then the lesser amount of product is your theoretical yield. You go check your pantry, you evaluate each reactant, And then the lesser amount of product is your theoretical yield. So why do we do two roadmaps? We have to check the pantry. And it's only after checking the pantry that we're able to say with confidence, hey guys, I can really only make 2 sandwiches based on what I got back there. Hey guys, I can really only make 27.36 grams of CS2 based on what I got. Questions? I see a question, second row. Yes, we checked our equation in the beginning, and as is, it was balanced, so everything is 1 to 1 to 1.
For the first one, on the left, the vertical axis corner, it's 1, and then for the second one, it's 0.36.
Because we had to evaluate, we had to go per root. We had to say 12 grams of carbon based on the mass and the moles gives us 1 mole. That's where that 1 comes from. The 0.36 comes from using the exact formula, but for sulfur instead. The ratio is 1 to 1. So if we have 2 moles of one, we have 2 moles of the other, 3 to 3, 4 to 4, 0.36 to 0.36. It's a 1 to 1 ratio. Okay? Yeah. So about the analogy? This page or this one? Okay. Yeah. Can you re-explain how you did that? Sure, right here. So to understand a little bit more about how we use this mathematical ratio or that approach, we want to be able to understand that when we're comparing two things, the example right here was aluminum and hydrogen, we know that the ratio between the two comes from the balanced equation. That's something we have over here, right? From the balanced equation, we're comparing aluminum and H2. We know that for every 2 moles of aluminum, we'll make 3 moles of H2, right? That's from the equation. That's what we know. Just like our sandwich analogy, we know this. So we can incorporate that into the ratios such that this is 2 to 3. These are just colons to represent ratios. What we don't know here, represented as our unknown, is based on the roadmap at this point, we knew we were dealing with 0.1234 moles of aluminum, and at the time, we didn't know how many moles of hydrogen we would need. So we incorporated that value, 0.1234, here, nicely lining it up. Everything on the left-hand side is about aluminum. Everything on the right-hand side is hydrogen. From there, this is basically a 2x2 cell, like a table. One of the things we're able to do is just like math, if we interpret it like fractions, we can cross multiply. The cross multiply tells us 2 times x is 2x. 3 times 3 times 0.1234. And then from there, it's just dividing both sides by 2 to get our final answer, x. One other way it can help to think about these math problems is to use real-world analogies. If, for example, we had chairs and tables, just comparing the two, let's say that every classroom is known to have 3 chairs for every 2 tables, right? You and I can do the math on that probably just by talking about it, right? 3 chairs, 2 tables. If we have 6 chairs, how many tables do we need? 4. If we have, for example, I don't know, 9, all right, so 3, 6, 9, 4, then we're going to need 6 tables. That's math that we can easily do in our heads, is based off of the analogies. But what if you just want to put a little bit more specific numbers into that? Let's say you have 6 here and we want to know how many tables. We cross multiply, we get 3x is equal to 6 times 2. 3x is equal to 12. Divide both sides by 3, x is equal to 4. So this setup just allows us to write down what our numbers are going around in our head in an easier way to understand, just by remembering known and unknown. If there's still an issue understanding the math about it, let's talk after class. Any other questions before I move on? All right. Our very, very last topic for today is a concept known as the limiting reactant. The limiting, oh, yeah, I see a hand. Sorry? Well, that was our understanding of why we needed to do 2 roadmaps. We evaluate each ingredient, compare the products. That was that topic right here. And now we're moving on to our final topic of the day, limiting reactants, abbreviated as LR. The limiting reactant, in short, is what bottlenecks the reaction. In essence, or really the big idea, is that once the limiting reactant is used up, the reaction stops, simply because there is no more to go. There's no more reactant left. The limiting reactant is the reactant that leads to the lesser amount of product. It is the reactant that leads to the lesser amount of product. So using this compared to the previous reaction we just did, in the previous reaction we just went over, the question was comparing carbon to CS2 and then sulfur to CS2. If I remember correct, let me just get the numbers. 12 grams of carbon was predicted to make 76 grams of CS2. 23 grams of sulfur was predicted to make, I believe that was 27.36. We had already previously identified the 27.36 as the theoretical yield, aka the lesser amount of product. So then which one is the limiting reactant? The sulfur. The limiting reactant is the reactant that leads to the lesser amount of product. We previously had deduced that CS2, the lesser amount, was 27.36. This is what tells us that the sulfur is the limiting reactant in this reaction. The limiting reactant is not something for you to calculate. It's simply for something for you to label / identify. You kind of saw this just earlier with the sandwich analogy, going back to the Czech pantry. Remember when we said that since we only had two slices of cheese, we could only make 2 sandwiches. Same thing for the meat. In this case, both the cheese and meat are limiting. Once they're done, we can't make any more sandwiches. Same idea applies here. The limiting reactant is the reactant that leads to the lesser amount of product. It is a term/label given to the reactant. Solely based on the term, you will never have a limiting product. Should make sense to you logically why a product can't limit a reaction. So only reactants can be limited. With that, we are officially ending module exam 2 content. We're going to stop lecture for today. Remember that Wednesday's lecture will be a practice problem session on today's topic. I do recommend taking some time to review today's topic. I'm sorry, not Wednesday, Thursday's topic. William turned around and I was like, holy crap, what did I just say that was wrong? Thursday is the problem session on this topic. Carry your calculators, carry anything that you might need. If you have any questions, you can come talk to me now. If not, I'll see you on Thursday. Yeah. Sure. Yeah, I upload them closer to the start of the exam.